Hi guys, welcome to JIK 224. I'm Dr. Sumia Sabal. This is the first video covering chapter 1, which is structure and stereochemistry of alkene. Okay, the first topic that we are going to cover is stabilities of cycloalkanes and ring strain. So upon completion of this topic, you should be able to explain how angle strain and torsional strain combine to give the total ring strain and compare the energies of cycloalkanes. Cycloalkanes are alkanes that contain rings of carbon atoms. Okay, so please recap back what you have learned from JIK 102. So some of the examples are cyclopropane with 3 carbon, cyclobutane with 4 carbon, cyclopentane 5 carbon, cyclohexane with 6 carbon, and cycloheptane with 7 carbon. So carbons of cycloalkanes are sp3 hybridized and thus requires an angle of 109.5 degree. So this is the optimum degree of a stable cycloalkanes. So 5 and 6 member rings are the common in nature. So later we will discuss why 5 and 6 members ring are the most stable cycloalkanes. And cycloalkanes do not have the same relative stability due to ring strain. Okay, if the compound is stable, then it means that it is low reactive. But if it's unstable, that means that it is highly reactive. It can involve breaking of bones and making of bones. Okay. So what is ring strain? Ring strain comprises angle strain that arises when bond angles of a cycloalkane carbon deviate from the optimum tetrahedral angle of 109.5. This strain is also called Bayer strain theories. Why? Because it was discovered by Adolf von Bayer, who is the first person who tried to explain the relative stabilities of cyclic molecules in the late 90s. And he was awarded with Nobel Prize for his work. And the second type of ring strain is torsional strain that arises when all the bonds are eclipsed. Eclipse is when it is in parallel to each other. Okay. So both strains increase the energy of the ring. Let's look at an example, cyclopropane, which is a 3-membered ring. Okay, the bond angles are compressed to 60 degree. See, from the optimum angle of 109.5 degree. So we have a compression of 49.5 angle compression from the optimum angle. This severe angle strains leads to nonlinear overlap of the sp3 orbitals and band bonds. So this is why cyclopropane is reactive. You can see here that cyclopropane also have all the CC bonds are eclipsed or are parallel, generating torsional strain that contributes to the total ring strain. Okay, and this is why cyclopropane is highly reactive, because the angle strain and the torsional strains contributes to the total ring strain. That makes it cyclopropane highly reactive. Okay. Apart from that, cycloalkanes with 4 carbons or more can adopt non-planar conformation. Okay, they are puckered or distort their shapes to reduce ring strains. So, because larger cycloalkanes have larger internal alkanes, so they can move or distort from their planar shapes, become a non-planar conformation. For example, cyclobutane, cyclopentane, okay, with 5-membered ring, cycloheptane with cycloheptane with 7 membered ring, and cyclodecane with 10 membered ring. Okay, they can the planar shape can become dissolved to become a non-planar conformation. Okay, cyclobutane is a 4-membered ring. Okay, so ring strain of a planar cyclobutane result from angle strain. Okay, because the angle here is 90 degrees, so we have an angle compression of 19.5 degree from the optimum 109.5 degree, and also because we have an eclipse of the bonds here. Okay, C1 to C2 and C3 to C4. So angle strain and torsional strain account for the reactivity of cyclobutane. And just now I said that more than 4-membered ring, it can have a non-planar conformation. So cyclobutane can have a non-planar conformation to relieve the strain. Okay, so cyclobutane adopt the folded conformation or an envelope to decrease the torsional strain caused by the eclipsing hydrogen. Okay, this is to relieve the strain. So you can see that the conformation now, okay, previously the degree is 90 degree here, the difference, but after it undergoes it folded, the degree reduces to 88 degree, and also the hydrogen now are no more, it is not eclipse anymore. Okay, so the hydrogen bond here is slightly moving and become non-parallel to each other. Okay, and you can compare these two illustrations can give a clearer picture of the Newman projection of non-planar and also a planar cyclobutane. You can see that the folding will relieve some of the eclipsing. Okay, so non-planar cyclobutane is more stable than a planar cyclobutane. Okay, what about cyclopentane? Cyclopentane is a 5-membered ring. So the conformation of cyclopentane is slightly folded, like the shape of an envelope, and this pocket conformation reduces the eclipsing of adjacent methylene groups. Okay, it also undergoes a folded conformation to relieve the eclipsing of bonds. Okay, so if you view from this angle, you can see that all the hydrogen are no more eclipse. Okay, and then cyclohexane. Cyclohexane is the most stable cycloalkanes. Why? Because cyclohexane is free from any ring strain. Okay, for example, this is a chair conformation of cyclohexane. So you can see that it has an optimum angle of 109.5 degree, and that all its hydrogen carbon are staggered. It is not eclipsed. So all bonds are staggered and therefore no torsional strain. And all bonds angle are near 109.5 degree, so no angle strain. And it does possess, however, a steric strain due to internal gauge interaction, but no more than 9-cyclic alkene. Okay, so how do chemists know that some of the cycloalkanes are stable and some are not? So what they did is through the calculation of heats of combustion. So heat of combustion is the relative stabilities of cycloalkanes we can determine from measuring the heat of combustion. So the amount of heat released when a compound is burned with an excess of oxygen in a sealed container called bomb calorimeter. Okay, So this is the general equation. We have the cycloalkanes and reacted in excess of hydrogen, oxygen. We can get carbon dioxide, water, and also the heat of combustion. So this is calculated based on the number of energy per methylene group. So if the compound has extra energy as a result of ring strain, the extra energy is released in the combustion. And the more heat per methylene group, the less stable the alkane is, or the cycloalkane is. So this is the table showing the heats of combustion per mole for some simple cycloalkanes. So we have here cyclopropane, cyclobutane, cyclopentane, cyclohexane, cycloheptane, and cyclooctane. Okay, so the values show large amount of ring strain in cyclopropane and cyclobutane. Okay, and while cyclopentane, cyclohexane, cycloheptane, and cyclooctane have much smaller amount of ring strain, and cyclohexane has no ring strain at all. So from here, you can see that cyclopropane, we can predict that cyclopropane is the most reactive cycloalkanes, and cyclohexane is the most stable cycloalkanes. So as a summary, two factors that contribute to ring strain is first, angle strain. This is caused when the angle has other angles than the optimum angle, which is 109.5 degree. So it can either have smaller angle or larger angle than 109.5 degree. Second, torsional strain, which arises when all the bonds are eclipsed or parallel to each other. And the lower the energy of the cycloalkane, the more stable the species is. This is the reference, and if you have any question, you can contact me at my email. Thank you.